As humans evolved, our brains learned to prioritize survival over absolute truth. We see solid objects, straight lines, and predictable motion because that's what helped us hunt, forage, and survive. But underneath that neat, practical illusion lies the true mechanics of reality. Zoom down to the absolute smallest building blocks of the universe, and everything we intuitively understand about how the physical world works completely falls apart. Today, researchers have begun harvesting these bizarre rules to build the next generation of global infrastructure, turning the chaotic behavior of particles into a technical blueprint. For nearly a century, the weirdness of the microscopic world sparked fierce arguments among physicists. Albert Einstein believed in a predictable, objective reality, arguing that particles should follow clear, logical paths. Niels Bohr argued the exact opposite. He proposed that light and matter exist as both waves and particles simultaneously, and that the mere act of observing them forces them to pick one form or the other. Bohr's theory won out, but researchers at MIT stripped this historical debate down to its absolute bare essentials to measure exactly how this transformation happens. In an idealized experiment, they isolated two atoms in a vacuum, holding them perfectly still with lasers, and fired a single photon at them. The moment the atoms registered its path, the rippling wave instantly collapsed into a solid point of impact. But capturing this delicate collapse required extreme conditions. The MIT team had to cool those atoms down to a fraction of a degree above absolute zero, which raises a very serious operational question. If these quantum states break apart the second they interact with anything warm or messy, how are engineers supposed to build actual functioning machines out of them? That exact problem led researchers at Brown University to try a completely different approach. Instead of freezing single atoms, they shifted their focus to engineering larger, more resilient structures. They hypothesized that if they built customized materials from the bottom up, piece by piece, they could manually lock these fragile behaviors into a stable physical state. Their building blocks are silver particles called Mecacons. By controlling heat during synthesis, they shaped them into 14-sided geometric forms, like microscopic Lego bricks. To make them stick, researchers coat them in flexible molecular chains, allowing the blocks to mesh precisely. Once combined, the rigid shape of the silver block and the flexibility of the molecular hairs force the particles to stack into entirely new, highly ordered crystal lattices. In standard metallurgy, when metals get heated, their atoms shift between different structural arrangements. There is an intermediate phase during that shift, but it is incredibly volatile and practically disappears the moment it forms. Because the Brown researchers precisely controlled the shape and stickiness of their Mecons, those blocks rapidly snap together, permanently stabilizing that elusive intermediate ghost phase. And that structural success revealed something even more surprising. When light hit this new silver lattice, the material exhibited deep, strong light-matter coupling. That means the electrons trapped inside those silver nanoparticles began oscillating in perfect synchrony with the passing light waves, becoming completely entangled with them. This is a highly sensitive entangled state that usually requires an absolute zero vacuum. But through pure structural engineering, scientists dragged that behavior into a warm, messy room temperature environment and kept it intact. While some researchers stabilize these states in physical matter, others harvest the underlying logic of the quantum realm to solve different macro problems. Today's blockchain-enabled Internet of Things networks connect millions of medical devices, sensors, and servers, making them sprawling targets for constant, sophisticated cyber attacks. This diagram shows a new approach to defending these systems. By mimicking the principles of the quantum world in software, computer scientists are optimizing artificial intelligence to secure these network interactions. They rely on a mathematical heuristic known as a quantum Chameleon Swarm optimizer. It models bits in quantum superposition to find efficient security paths. Looking at the bottom half of the diagram, this quantum logic feeds deep learning models, allowing AI to instantly isolate complex intrusions. It is a massive leap in scale. We started with a single photon, isolated in a freezing, dark vacuum, behaving in ways that defy our natural intuition. But then we track that behavior up to the nanoscale, using custom silver blocks to force those rules into our warm, room-temperature reality, and eventually deploying that same logic across global computer algorithms. The century-old paradoxes of the double-slit experiment are moving beyond the blackboard. appearing as room temperature materials and the algorithms securing our global data.